So we took these symmetry representations that describe everything within the point group. We applied it to vibrational spectroscopy. Okay, so we can see what stuff is, what particular modes, what sort of nature of those modes are, right? Which is fine. But really, one of the reasons why symmetry is awesome is because it really simplifies and helps us better understand molecular orbital theory. Okay. Again, I'm not going to spend a lot of time on MO theory. You get much better information from other classes. I'm going to give you this much. But where I want you to focus is how the symmetry allows us to show how those particular orbitals are able to interact. Right? So one of the things we're going to turn to for this are something called symmetry-adapted linear combinations of atomic orbitals. Okay? When you have atomic orbitals in a point group that then form molecular orbitals, the symmetry of the atomic orbitals is now placed down in this three-dimensional framework. And all of the symmetry operations that we do are then operating upon your atomic orbitals. And so what that means is that those combinations of orbitals, how you add and subtract them, linear combinations, adding them in phase or out of phase or what have you, has a symmetry characteristic. And what we find is that only when they have the same symmetry species will they be able to combine. So that's what we've been building up to this whole time. And so we're going to use these symmetry-adapted linear combinations to choose what orbitals are interacting with which orbitals. Right? So sulks are wave functions that you combine into what we call a group orbital, where psi represents the wave function of the same symmetry class. The overall wave function between a group of orbitals, it's a combination of a weighting function, the atomic orbitals themselves, and an overlap. And so we can look at the combination of these orbitals, and what we find is that as long as they have, as long as this is non-zero, they can combine, and this only happens when they have the same symmetry species. So how do we find those symmetry species? Well, it turns out that we treat the orbitals pretty much in the exact same way that we treat vibrations or atoms. So we place them in there and we look at how they transform. So let's take a look at the p orbitals on NO2. All right, we're going to look at the oxygen-only atoms. So we're only going to look. So this is. I'm not going to draw anything on the board. We're going to do this old school, the chemistry tool. Okay. NO2 is a bent molecule. Right? It has a point group of C2V. The nitrogen is in the middle and the two oxygens. And so the x-axis would have orbitals pointing out of the x-axis here, right? And so coming towards you in this case, and the z-axis would be up, x, y, z. And so those px orbitals are in and out of the plane for us, for our example. So we can build a reduced representation for those orbitals and talk about what happens when we do the symmetry operations. So it turns out that the way you do this, you treat them exactly like vibrational modes to figure out what their behaviors are. We actually did this for a number of species, but let's do it again. So we treat these in a similar way that we did to orbitals, and so we ask, how does it change? Okay, how do the atoms change? How do they rotate? Are they symmetric? Are they anti-symmetric? And so we have the two of them. And for the identity operation, those two are unchanged, and so they're both symmetric. So that would be one atom symmetric, another atom symmetric, that would be two. Right? So what about the C2? Well, in this case, we rotate them. And again, we're talking about the orbitals, and so the orbitals are rotating, and so we turn them, and the thing turns around, and so both of them become changed. They moved, and when you move them, they have a character of 0. Okay, we can look at the XZ mirror, right? And so it runs along the x-plane, along the x-axis, and so this would flip those, and that would also be 0. And the YZ would, regardless, would reverse the atoms, flip them, and so they would be -2. Right? So these flip those axes, that flip that x-axis, and so these would represent the reduced representation for this particular system, right? 2, 0, 0, -2. And so what we can then do is we can extract out the irreducible representation that make that up. Right? And so we can see that this is a linear combination of the A2 and the B1. Right? The A2 and the B1 would represent the two different ways you could arrange p orbitals. Right? And that's the long way. We could do the simpler way. If you actually look at the symmetry of the orbitals, they are fairly symmetric. There's a figure 6.22 in your book that represents the A2 symmetry version of this, where you have one has the p orbital where the signs are aligned, and the other one has the p orbital where the signs are anti-aligned. That's the only two ways you can really arrange those two orbitals. And in that symmetry operation, you'll see that the one that has them anti-arrangement, that one matches an A2 symmetry species. So it's A2. And the B1, on the other hand, would represent where they're both aligned. Right? So this represents what we call a symmetry-adapted linear combination. We've combined those orbitals in two ways. This is a long, drawn-out process, especially when you get to 3, 4 atoms. But your book has already done it for you. At the back of your book are these little pictures that represent symmetry-adapted linear combinations. So in the back of your book, right around page 857, you can see for the C2V point group, looking down on the A2, you see that the A2 and the B1 would represent two types of p orbitals, px in this case, aligned along perpendicular to the z-axis, and you can see that that's the only two ways you can arrange them. So let's take a look at another example. Let's do the same basic analysis for water. You can do this for water, again, with hydrogen. We're going to use water. We're going to combine all the orbitals for water. Again, it's C2V. You can see that the group orbitals for hydrogen are A1 and B2. All right, A1 and B2. And those that are both symmetric and those that are anti-symmetric, and you can prove this to yourself, or you can look it up, and so you can see that, and notice it's a different symmetry set for the s orbitals rather than p orbitals, but that's to be expected. Now, what's going to happen here is that now that we know the symmetry species for these two different groups, this is the two different ways you can arrange those hydrogen orbitals. Right? We can then compare it to the oxygen. Right? So for the oxygen, it's on the origin, it's on the principal axis, and so it transforms like the character table. And so we see that the s orbitals are going to be A1, the 1s and the 2s are going to be A1 symmetry. And the x, y orbitals are going to transform as B1 and B2 respectively, and then the PZ is going to transform as A1 as well. Okay. So we can see that the s, any of the s orbitals and the PZ orbitals will transform as A1, and everything else will be B1 and B2, which automatically tells us information about what's going on. The B2s are going to overlap in one way, and the A1s are going to overlap in another with the system. And this x orbital is going to do other things. How do we know which ones will overlap? So it turns out that this weighting factor depends really on the energy difference in the orbitals. The energy difference of the orbitals, if it's really large, then this drops out, which means that the orbitals they're not of the right energy to overlap with one another. We can see this in our structure. Okay, so some of the 2s orbitals. So then we know that this A1 orbital is going to interact with the s orbitals and the p, and we can start to build up a picture of what's going on. Now the actual energies we are not going to do. We are not going to construct the orbitals in this way. We're not going to arrange them in energy. We see that the 2s orbital mixes in at lots of different energy levels with, and the A1 group mixes in. And so the group orbitals then behave in a similar way to our oxygen orbitals. And we did things with molecular orbital pictures. Right? And so we can then see that the new molecular orbitals will then have the symmetry of the group. A1 and B2, or A1 and B1, or what have you, when they combine. All right. Notice how the 1B1 is a non-bonding molecular orbital, doesn't stays with the p orbitals. It is essentially that p orbital above and below the plane. Oddly, we don't think about that when we talk about water. We don't think about that orbital. Because we invoke hybridization, which hybridization takes advantage of many of these factors. So let's do it one more time. Let's do it for the hydrogens on an ammonia. All right, so we can see that those three hydrogens, we do the identity. They are going to all move. They're not going to move, so that's 3 of them. All right, and then we do a C3. A C3 rotation turns them all, so that'll drop to 0. All right, so that means that they're all 0 now. The mirror plane will move 2 of them, and the other one will stay where it's at. And so we can, from this reduced representation, we can see that you end up with the following reduced representation. And from that reduced representation, we can reduce it down to irreducible representations, and we see that those irreducible representations would be 1E combination, which is doubly degenerate, and then an A1. All right, so we could think of the new group the group of hydrogens has 3 distinct forms. All right? One has symmetry A1, and then there's the 2 doubly degenerate E symmetry forms. The shape of which, again, you can figure out from how much it contributes, like how you subtract those orbitals together, but it's easier just to go to the book and look at what the E's actual shape is. All right, so they're all going to be exactly the same. One of them is going to be different sign. than the other, and so then how can you combine those? Well, you can have cancellation, you can have, but they all have to balance out. So the actual weightings here are less important. But again, someone has gone through this laborious process for you and has generated these symmetry adaptive linear combinations. You can look in the back of your book. You put three spherically symmetrical objects like around a C3b, and that's what you get. Now comes the fun part. You can see that this allows you to, one of these is A1 and the other two are E, and then if you look, the A1 would be on the nitrogen. We see that this has a PZ orbital. So the PZ would overlap with these. There would be some S character too. One of the S orbitals would overlap, but we can see that the PZ orbital would interact with these hydrogens, right, to form a bond of sorts, a molecular orbital. And then the PX and the PY would interact with these. And you can actually see that your book has some lovely pictures where it actually shows you how they overlap in a positive way. On page 203. And that's what it tells you. So you can say how the orbitals are interacting with various symmetry adaptive linear combinations, and then from there build up a molecular orbital diagram, or knowing the symmetry of those talk about the symmetry of the molecular orbitals that are generated. So that's all we're going to be able to squeeze out of symmetry in this weird end of the semester thing. So there you go.